So, recalling our connection between polar and rectangular coordinates, whenever we're talking about things in terms of one or the other, we can always translate to the one we aren't specifically looking at. Now, as I said when we were talking about these things initially, some situations are kind of better designed for being talked about in terms of one coordinate scheme over the other, but it is good to know that we can always translate if we need it. When we're looking at these points, when we're looking at these equations, we're looking at really anything, we can always build off of the relationships that because x over r equals cosine of theta, we have x equals r cosine. Because y over r equals sine of theta, we have y equals r sine theta, and x over y will thus equal tangent of theta. While if we want to think in terms of distance or in terms of circles for that matter, we can also always say that x squared plus y squared is equal to r squared. And we can use this for translations in either direction. For example, to start off, if we want to find the rectangular coordinates for the point in the polar plane given by -2 pi, well, we have -2 pi equals r theta, so r equals -2, and theta is equal to pi in this case. And from here, all we have to do is just apply our formulas. We want to find x and y. Well, x is r cosine theta, which here is -2 times cosine of pi, where cosine of pi is equal to -1, so r is 2. Similarly, y is r sine theta, so we will have -2 times sine of pi. Sine of pi is 0. So, thinking about that point that we saw earlier, thinking about this guy right here, -2 pi, as we might expect, if we want to represent this in the rectangular plane, we will have the unique coordinate 2, 0. And it's important to remember here that when we're talking about the rectangular plane, we have a single representation for that point, because that's the kind of relationship we like to work with in rectangular coordinates. But in polar, that's one of many ways we can talk about that location. We could actually talk about the location also as 2, 0 if we wanted to, but choosing a less obvious one in this case. In our next example, we're going to see essentially how you can go in the other direction. That is, how we can go from rectangular to a representation in polar. So for this, we want to find a polar point with the rectangular coordinates 1, -3. So first, just for the sake of clarity, we may want to actually make a picture of what it is we're looking at here. We may want to understand roughly the shape of what we're looking at in terms of a location. From here, we need our values for r and theta using the fact that we have x, y equals 1, -3, so x equals 1 and y equals -3. If we want to get r, we have our distance relationship, r squared equals x squared plus y squared, which here is 1 squared plus -√3 squared. It's a bit long-winded, but we get 1 plus 3, or 4. And from here, we take the square roots to get that r is equal to 2. Technically speaking, r is equal to plus or minus 2. And again, that brings up the idea that we don't have a single way to represent a point in polar coordinates. But usually, when we're doing these problems, we make r positive unless you have a good reason not to. Here, we're going to the right anyway, so why make life more complicated? we'll take the positive root. Anyway, we've got r. Now we need theta. Well, to get theta, we'll use tangent. That is, if we want to get theta, we have tangent of theta is equal to y over x, which here is negative root 3 over 1, or negative root 3. So if we want to find theta, we need to know where tangent is negative root 3. That is, we want the value in the fourth quadrant in this case, since we're coming all the way down to there, as our picture says, or 5 pi over 3, which says, just to be sure, that one way we can represent this point is 2 5 pi over 3. Now this is one way we could handle that representation. Like we saw earlier, we could make this negative, add more rotation for absolutely no reason, change how we want to relate this, but here is one way that we can represent our point in polar coordinates, like so, using that radius at angle. And next, we're going to look at how we can extend these ideas to talk about not just points, but equations.